All right, good morning, class. This is lesson number 7, so day 7, lesson 7. We are covering section 1.9 of our textbook today. 1.9 largely, this is our last section of chapter 1. We have all this new vocabulary we've been introduced to in this chapter. And chapter 1 here is really going to finish things off with, there's some last few things we want to talk about with transformations, different types of transformations, how we can tell what a transformation is doing, and furthermore, how we can pull a transformation apart. This is going to use things like linear combinations, which we've seen before, we've studied before. So really, all that's new is just taking transformations as we have them and really dissecting them a little bit more. That's what we're doing today. So let's go ahead and take a look at some different types of linear transformations. First of all, I want to highlight this special matrix that we keep kind of seeing pop up in different examples. I've told you a little bit about why it's important, but we haven't talked a lot about it just yet. We know in R2, let's see, let me make sure that's on the screen. Okay, good. We know that in R2, any vector, I'll call it U, in R2, we know then that U looks like this. And we know every single vector in R2 can be written as a combination of these special guys, right? But notice this linear combination I can also rewrite as matrix multiplication. What is this multiplication then? Well, this is 1, 0, 0, 1. Times the vector x. What's going on here is that they take this matrix and multiply it times any vector, I get that same vector back, right? In other words, this is called an identity matrix. What is an identity matrix? Basically, for matrices, this is acting like the number 1. So I'm going to put in quotations, acting like the number 1. Right? What do I mean by this? Well, think about regular real numbers. If I have 1 times x, that's just x, right? But now in matrix multiplication, the identity matrix times any vector u, any vector, and notice this x was just any real number up here. Any vector u, it's just going to give me back u. So this identity matrix acts like multiplying 1. Now I want to clarify this here because I've seen students in the past where they see the identity matrix and they just change it to number 1. The identity matrix does not equal 1. Right? The number 1 is a real number. The identity matrix is a matrix. These two things are not equal, so watch out for that. I've seen students do that before on tests, midterms, homeworks. You will lose points for this. These are not equal, right? They act the same. They do the same thing in multiplication, but they are, in fact, different objects, right? So this is called an number 1. We can use notation. We can call the identity matrix capital I for identity. So we can rewrite the identity matrix as this capital I, but again, this is not equal to the number 1. So again, watch out for that. This is going to be more important later when we start talking about how we can solve matrix equations by multiplying or dividing things over. That's coming later. I believe That's somewhere in chapter 2 or chapter 3. So we'll get there. But I want to highlight this. The identity matrix is not the number 1. Watch out for this. Students make this mistake and then they lose points for it. So be careful here. All right. So what am I bringing this up for? Well, the identity matrix, this was for R2, right? Well, you can guess the identity matrix in R3 is going to follow the exact same pattern, right? In R3, the identity matrix, and I'll use subscript 3 here. So I subscript 3, in other words, the identity matrix in R3 is going to be the same kind of idea. I have a vector going in the x-axis direction, a vector going in the y-axis direction, a vector going in the y-axis, or sorry, z-axis direction, right? A horizontal, a vertical, and then a, if you want to think about it three-dimensionally, you could think of x and y being on the board, and z is like a new axis that can come towards the screen or it can go backwards behind this board. And then it becomes three-dimensional, right? You have 3 axes in R3, and so you need a vector to be able to travel in each direction. But just like this identity matrix, note, I have a pivot in every column. Note, these vectors are linearly independent. There's no free variables. But also, this has the special property that any vector in R3 is just a combination of these 3 vectors, right? And in fact, I don't have to change anything. I can just take these constants, right? So what I'm getting at here is every single identity matrix is going to be of this form. All that's different is what dimension space are you working in. So again, to introduce some notation, because this is going to be important for a theorem later, I'm going to put in the notes for today. We can further abbreviate this where we're going to use E1 to be one of these identity vectors or one of these column vectors in the identity matrix, where E1 is just going to be, I'm going to put 1 in the first entry. That's what the subscript 1 means. E2, I'm then going to put 1 in the second entry. And so I can rewrite I2 as being the matrix with E1 and E2 as columns. Well, in fact, any size identity matrix, I can do this. If I'm in R3, I can say I3 is the identity matrix with E1, E2, E3, where E1, E2, and E3, you're going to have to increase the number of entries just depending on what space you're inside of. Because this is in R3, well, now E1 has 3 entries, but I'm going to put the 1 in the first spot. That's E1. E2 has 3 entries, but I'm going to put the 1 in the second spot. And then E3 has 3 entries, and I'm going to put the 1 in the third spot. This notation is going to be more important in a few minutes. Okay, so what am I getting at? Why is this notation helpful? Why do we care about trying to learn this new notation? Well, let's look at an example using transformations. This new black marker I got is really sticking to the board. It's not erasing very well. Or maybe I need a new eraser or a new board. Who knows? Could be any of the above. Okay. The blue marker seems to be doing better. Or you know what? Let me switch to this other eraser. It might erase better. Okay. So let's look at an example using transformations. Let's say T, so this is an example. Let's say T is a transformation from R2 into R3, right? So my x's, my domain vectors, come from R2. They're being sent to R3. So automatically, we know for this transformation, my matrix A is a 3 by 2, right? So don't forget that fact from last lesson. This is going to be important as we continue in the class. Okay. But now let's suppose that I don't tell you what the matrix is. And instead, all I say is that, well, I'm going to tell you when you plug in the first identity vector, you're going to get 5 negative 1 identity vector 0. And let's see, let me make sure that's still on the board. Okay, perfect, right? So these are the facts we have to work with. What can we tell from this? Can we find the matrix A? Can we find what is T of X equal to for any arbitrary vector X, right? Let's work with this second question first. Can I figure out what happens when I plug in some X? Well, every X in R2 is a column vector with 2 entries, right? Where X1 and X2 are real numbers. Okay. I don't know what this is, but I do know, because these are the identity vectors for R2, I do know that X equals X1 times E1 plus X2 times E2, right? Just like we said in the past thing here before I erased it. Every vector in R2 is a linear combination of the first column of the identity matrix and the second column of the identity matrix, E1 and E2. So how can I use this? I would like to figure out what is T of X for any arbitrary X. Well, let's plug in what we have here. We have then T of X1 E1 plus X2 E2. Okay, fine. How does that help us? Well, remember from at the end of last class, we talked about transformations. In fact, matrix transformations like this are linear. Because they have the linearity property, that means I can distribute this t over plus signs. Just like the integral, just like the derivative, those transformations are also linear transformations. So I can distribute this, and now I have t of x1 e1 plus t of x2 e2. But also remember, x1 and x2 are just real number constants, right? Whatever they are, they're just some constant. I can pull constants outside of the transformation. Skipping ahead of myself. All right, so I can pull these constants out. So even though I don't know what X is, even though I don't know what the matrix A is, I can still use these facts to try to piece together what's happening here. So this then is a combination, and I'll write it over here. So T of X is this combination of these vectors. T of E1 is 5, negative 7, 1. T of E2 is negative 3, 8, 0, right? But this is just a linear combination, right? So there's 2 ways I can write this. One, I could pull this apart into matrix multiplication, since all linear combinations are or is matrix multiplication. We have 5, -7, 1, -3, 8, 0 times x1, x2. In other words, I've rewritten t of x as a matrix times x. Well, lo and behold, without even really trying to, I just found the matrix A, right? So we just answered this first part of the question. But then two, what is t of x equal to? Well, now I can multiply this out. I can multiply, add these together. I can do the dot product. And we're going to have 5x1 minus 3x2 -7x1 plus 8x2 x1. Copy that right? Yeah. Right. So here's t of x. A single vector. This is the output. I've answered both pieces of the question just like it's supposed to be. Now, what's special here? What's the point of this example? What am I trying to highlight? Well, look what happened. For linear transformations, when you plug in your first identity column, your second identity column, that's going to be telling you exactly what your first column and second column of matrix A are. In other words, the matrix A was the transformation where each column was T of E1, T of E2, right? See how this happened here? So in fact, you can use the identity columns to figure out what your matrix A transformation is by plugging them into T, or if the problem tells you what they are, then that means the problem is telling you the matrix A. You just have to piece together what that means, right? Okay. Why does this work, though? And we saw it worked out in this example. Why does this work in more general terms? Why is this going to work all the time? Well, notice here, forget about this for a moment. What is T of E1? Well, T of E1 has to be the matrix A times the first identity column, right? Now, the matrix A, whatever it is, we know A is a 3 by 2. And so the matrix A has a first column, a second column, and a third column, right? Or sorry, there's only 2 columns because it's 3 by 2. It has a first column and a second column, where each column has 3 entries because it's a 3 by 2. Well, what is this then? This is going to be A1, A2. In other words, A1, A2 times 1, 0. But if I do this linear combination, this is just 1 times A1. A1 is the first. Here from this formula, T of E1 equals the first column of A for exactly this fact right here. We're just rewriting this as a matrix equation, rewriting it as a linear combination, and lo and behold, T of E1 is the first column. For the exact same reason, T of E2 is the second column of A. So we can use this fact to piece together what the matrix A is. All right, this is going to lead us to one of our first big theorems. Now, this theorem doesn't specifically have a name in the textbook. The textbook might have like some kind of numbers associated with it, like it might be section 1.9 theorem, blah, blah, blah. It'll be some number. When it comes to like the homeworks or the tests, no, I'm not going to expect you to memorize the theorem number. You can just use this fact, this theorem I'm about to write. You don't really have to say by theorem so-and-so. You can just say, yeah, this is a fact, right? We can use this fact. There will be later, we'll have some theorems that are actually named, theorems that have special names that aren't just a number. Those named theorems, you will have to remember and reference those. But for any of these theorems that don't have like some special name, don't worry about trying to memorize what number they are in the textbook. That's not a big deal. That's not what I want you to memorize. Instead, I just want you to memorize this idea that's in the theorem. So what does the theorem say? So theorem, we have given a transformation, given t from Rn into Rm is a, we have then that then there exists a unique this is going to be an m by n matrix A. Note again, look here, I'm flipping these numbers to figure out what dimensions are for the matrix A. So there exists this matrix A. Not only does a matrix A exist, but it's a unique matrix A. So there's only this one matrix A which does the job, such that for any x in my domain, T of x equals this matrix A times x, right? Which again, so far, this is just regurgitating what we've already said about transformations. There's nothing new here yet. Here's the new piece, where I can now give you a formula to find the matrix A. The matrix A is going to be where the first column is plug in the first identity column to T. If you know what this is, that's the first column of A. If you can plug in the second identity column, that tells you the second column of A. Dot, dot, dot. How many are there? Well, A is an M by N, so there are N columns. So you'll need to go up to En. Right? Why? Well, again, these are the identity vectors that are associated with the space that X is inside of, right? So it has to be N of them. And we also know A has to have N columns. So that's where we're getting this formula, where for any I less than or equal to N, so I'm looking at any of these indexes that are less than or equal to N, EI is the ith column of the identity matrix for Rn, right? Which is exactly the definition we had for these guys. E1, E2, E3, E4, so on. These are the columns of the identity matrix. They're the ith column of the associated identity matrix. Furthermore, A is called the standard matrix. So you can see some questions in the homeworks if you want to work through some of those exercises just for practice. They're going to ask questions about finding the standard matrix. This is what they're referring to. This is just another way of saying find the matrix A, right? Except now we've given a formal name to the matrix A. It's called the standard matrix. Okay, I'll leave that there for just a moment. So we can now start to think about like, okay, what if I give you some other transformation? I don't tell you what the matrix A is, but I tell you what I want the transformation to do. Can we figure out the matrix A? Well, let's take a look. using this theorem. This theorem is going to be super important, so make sure you do remember this. You want to memorize this. It's going to be very helpful. If a problem gives you T of E1, T of E2, dot, 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 so on, the problem is telling you what the matrix A is. So make use of that fact to get your matrix A. It's going to be very helpful in homework problems as well as test problems. All right. Okay. So let's take a look at some examples, how we can use this theorem. So let's say that, I want some transformation which is going to stretch my vectors. I want a transformation that's going to make my vectors longer, bigger, right? I want to stretch it out. And I tell you that I want this transformation to change the vector x. I want it to become 3 times bigger, right? And this is for any x in R2. Okay. Well, I've written this transformation as just the vector is getting scaled, right? But I want to know, what is the standard matrix? What is the standard matrix? Well, how can I find it? According to the theorem I just had on the board, A equals T of E1, T of E2, right? Now, first of all, before we continue, we also need to verify, before I can even find a matrix, before I do this step, I first need to find out, is T linear? In other words, does this T obey the linearity property? Because if it's not linear, if T is not linear, then A does not exist. So this is kind of a first check we have to make here. Why? Well, if you have a transformation that's using a matrix A, that's a matrix transformation, it is automatically linear because all matrix transformations are linear. But if it's not linear, that means it's not a matrix transformation, which means don't even bother. There is no matrix A, right? So this is a key thing we need to check first. Is it linear? Well, how do I find out if it's linear? There were 2 things we have to check for linearity. One, I need to see, if I take a vector and I multiply it by some constant scalar, can I pull the scalar outside, right? I need to know if this is possible. Okay, so how do I check? Well, let x be in R2. This is an arbitrary vector. And let C be in R. C is now some fixed arbitrary constant. So now I want to check, okay, what is T of Cx? What T Cx of all, x is a vector. Transformation T says whatever is in here in the parentheses, I want to multiply it by 3. So this is 3 times C times the vector x, right? But what else can I do with this? Well, 3 and C are both just real constant numbers, right? And we know when you're multiplying real numbers, 3 times C is the same thing as C times 3, right? So I can flip the order, and that's fine. It didn't change anything. But now what happens? Well, 3 times x is just T of x. I have C on the outside, and lo and behold, I have exactly what I want, right? So does it pass this first check for linearity? Can I pull out constants? Yes, I can pull out any arbitrary constant. So when you're trying to check for linearity, you have to pick an arbitrary vector x and an arbitrary constant. You can't pick a specific x and say, oh, look, it works for this one example of x. That's not a proof. To prove it's linear, you have to say, think about an arbitrary vector x. I don't know what this vector x is. I'm not going to pick a specific example, because what if you pick a specific example that it just happens to work for, but it doesn't work for others, right? So we have to leave this x arbitrary. And for the same reason, this constant has to be left arbitrary. So this shows the first property of linearity holds. Okay, good. Now what? Well, now we need to check, can I distribute t over when I have multiple vectors being added together? So let u and v be in R2. These are two different vectors. And we want to check, we want to show, if I have t of u plus v, can I distribute the t? Can I pull this apart into t of u plus t of v, right? This is the question we're trying to answer now. All right, well, what is t of u plus v? All right, well, u plus v is just some new vector. According to the transformation, I have to multiply it by 3. So this is 3 times u plus v. But remember, when you have a scalar times two vectors being added together, you can just this 3. Right? So this is, well, in fact, lo and behold, what is this? Okay, so great. We've shown that the linearity properties hold. And in practice, did this take a lot of time or a lot of work to show? No. In both cases, this was like a one-line thing. I'm just double checking, is it linear? As long as it's linear, we're golden. If, however, it happens to break one of these properties, then it is not linear and you cannot find a matrix A. So this is kind of a important step you have to check in order to find the matrix A, or in order to know if matrix A exists at all. All right, so we know it's linear. Now we can move forward with trying to find matrix A. Well, now we can just use that theorem we had from before. I need to figure out, what is t of e1? Well, t of e1 is going to be 3 times the first column of the identity matrix. That's 3, 0. T of e2 is going to be 3 times the second column of the identity matrix. That's just 0, 3. In other words, my matrix A is just, it looks the same thing as my identity matrix, except it's been multiplied by 3. So what is this matrix doing? It's taking my x value, it's tripling it. It's taking my y value, it's tripling it, right? This is the matrix I want. And so we have, in fact, that for this matrix A, t of x, which equals 3 times x, is the same thing as a times x, right? This type of transformation is called a dilation. This transformation is called a dilation, right? So this is one kind of special transformation. What is a dilation? This is just something that stretches a vector, or if this were a fraction like 1/2, it could shrink it down. Or if it were like -1, then it would reflect it in the opposite direction, right? This is called a dilation then, stretching and squishing of the vector. Why do we care about these kind of transformations? Well, one application you could imagine is you could think about something like Photoshop. Okay, why am I bringing up Photoshop? Well, Photoshop is all about modifying, editing pictures, trying to make them look however you want them to look, right? Well, a picture is really just process that data into a new image or a new block of data that looks the way you want it to. In other words, a picture, any picture you have, we know, if you know anything about pictures or computers, an image you can think of as like an array of pixels, right? Where each pixel has an associated red, green, blue value, right? That red, green, blue value is telling you what is happening for that pixel. It's what's happening for each pixel, and together that forms your picture. Well, in other words, you can think of a picture as a matrix of red, green, blue values. And so if you want to modify that picture, it's the same thing as modifying its matrix of red, green, blue values, right? So Photoshop in the background, whoever designed or programmed it or created the application, in the background, when like you're stretching things on the computer or you're changing colors or something, that's instantaneously in the background in the code doing matrix transformations, and it's just showing you the visual change, the visual result of that matrix transformation, right? So if you're somebody who you want to design like the next and greatest best Photoshop, you got to know how to program matrix transformations, right? This is why this kind of section, why this class is super key, especially for anyone in computer science. As you continue, you're going to find any kind of data manipulation is oftentimes going to be some kind of matrix manipulation, right? This is why we spend so much time, why we have an entire class dedicated to just talking about matrices. Okay, enough of that. I'll get off of my soapbox. Let's continue. Wanted to highlight that is one application where they could pop up. If you're not a computer science or chemistry, the point here is that any manipulation of data, if you can organize your data in some kind of array or matrix or table, and you want to manipulate that table or matrix in some way, that's going to be some kind of linear algebra manipulation, right? So, okay. Let's continue then. Of course, there are other types of transformations. You can like rotate a picture. If you're going to rotate things, that means you're changing the angle of stuff. That's going to be using some trigonometry. For the sake of time, I'm not going to go over that specifically, and I want to cover some other topics. But if you want to see some examples that are talking about rotations, it's in the textbook. There's also a brief example in the lecture notes on Canvas if you go to section 1.9. I don't want to spend a lot of time on that, though. It's just another example, just like the dilation. At any rate, okay, let's continue. What I really want to finish highlighting for this class today is some special properties of transformations. We've seen that, okay, you know, whether or not a transformation has a solution can determine whether or not a linear combination exists, whether or not an X exists that you can plug in to get to a B, right? Linear transformations, we have this formula. When you plug in an A, or when you plug in a vector X, multiply it with A, you get a brand new vector B. T is a transformation from some Rn into Rm. Our X is inside of the domain. And the B is inside of the codomain, right? So this is just copying the diagram we had from before, from yesterday. Sorry, I needed some water. All this talking nonstop dries out my my throat. All right. We have this idea here, right? Now, one thing we might like is, do we have a solution for all possible B? Does a solution exist for all possible B in the codomain Rm? If we do, that means the range, the entire domain, is all of the codomain, right? That means for all of my inputs, there's some input that would allow me to reach any possible vector in the codomain here, right? If if a solution doesn't exist for all B, so if we don't, then the range is not all of the codomain because it missed some B. There's some B in there which no solution exists. There's some B that no matter what X I plug in, I can't reach it. I can't hit it. So in that case, my range is instead just a subset and not equal. This is notation for a subset which is not equal. It's strictly smaller than, it's strictly contained inside of Rm, right? Well, in fact, this is going to give rise to one of our definitions. So here's a new definition. We're going to say T from Rn into Rm is called an onto transformation. Now, if you've taken like some other math classes, or if you've taken some analysis classes, onto, this is the same thing as surjective, right? So say a function is surjective, is the same thing as saying function is on. They mean the same thing, right? So I'm just putting this word here in case you've seen it before, so you can connect those previous ideas, those previous definitions. Okay, so T is called an onto transformation if for any B in my codomain, there exists at least one X. Note, it doesn't have to be only one. I'm just saying at least one X exists. At least one X in the domain exists such that when I plug in that X, I get that B. In other words, this is saying for any possible B, a solution exists. Maybe there's infinitely many solutions. It doesn't have to be just one. It says at least one, right? So a function is going to be called onto if for any B in Rm, there exists at least one X in Rn such that T of X equals B, right? In other words, for anything in the codomain, there exists a corresponding input which gets mapped to it. Now we're going to have space to write that here, but if you look in the lecture notes for 1.9, I also added that sentence in quotation marks. For anything in the codomain, there exists a corresponding input which is going to get mapped to it, right? It's going to get mapped to that thing in the codomain. Okay, this is called onto, this is called surjective, right? Well, we can also have idea of when is a so here class or a calculus class, a function being one-to-one is the same thing. So just a brief little review. A function such as the line y equals x is called one-to-one in part because it passes the horizontal line test, right? Passing the horizontal line test for functions in R2 is the same thing as one-to-one, right? What was the point in order to be one-to-one? Well, we're saying no matter what x's you plug in, no matter what x's you plug in, there are no two x's that get mapped to the same spot, right? There are no two x's that get mapped to the same spot. So on2 would say, well, for every possible b in Rm, there's a solution. So for any b, there's a solution. But one-to-one would say, well, if I have two different x's in my domain, they never go to the same spot. They're going to go to different places. So they're going to satisfy the horizontal line test. So we don't have a horizontal line test we can do with matrices because we can't really graph a matrix equation in the same way. I mean, I suppose you could like graph planes and things in R3 or R4 or something, and then you can kind of check like, oh, does this pass or something, right? But I think trying to graph it at this stage when we're dealing with matrices is a lot more work than it's worth, and it's just easier to get used to this definition I'm about to put. So what does it mean? Rn into Rm, a one-to-one transformation if I'm gonna word this similarly to our on2 definition. If for any b in Rm, there is at most one x in the domain such that t of x equals b. Now notice the key difference here. For on2, I said there had to exist at least one solution for any b, whereas one-to-one says there has to exist at most one. So first of all, for any given output, I can't have more than one x that goes to the same place. But I can also, at most one, that means I can also have 0 solutions, right? There is at most one x such that t of x equals b, or there can be 0x such that t of x equals b, meaning there could be b for which there is no solution, right? So one-to-one does not necessarily imply on2 because it could be possible that for one of these b's, there's no solution, right? But for the same reason, or for a similar reason, on2 does not imply with more than one solution. I could have a b with infinitely many solutions, in which case I'd have a bunch of different x's going to the same place, and it would break one-to-one. So on2 and one-to-one are really separate definitions. They're separate properties. One does not imply the other. They're separate from one another. So here the idea for on2, we said for anything in the codomain, there exists at least something in the domain. There exists some input that can be mapped to it. Whereas for one-to-one, we're saying for any output, it doesn't have to be everything in the codomain. We're just talking about the range. For any output, for anything in the range, for any possible output, there is only one corresponding input. This does not require only one input to an output. This does, right? Now, partly what I'm getting at is that one-to-one, because it never allows multiple solutions to occur, that means one-to-one is the same thing as saying no free variables, right? In other words, there's a pivot in every column of A, right? Now I'm going to write out these theorems here because I'm running out of space. This is the last thing we're going to do for today, and we'll look at participation day 7, I think it is. But participation day 7 is going to use these theorems that I'm writing right now. So here's a theorem. This theorem doesn't have a name, but it's a theorem that we can make use of. You can just use this as a fact, and it's going to be very helpful if you're trying to tell if a transformation is one-to-one or not. So T is one-to-one if and only if. Recall this phrasing, if and only if, is just a fancy term for the implication goes both ways. T is one-to-one implies what I'm about to say, and what I'm about to say implies T is one-to-one. The implication goes both directions, okay? If and only if, so we just said here, in order to guarantee there are no multiple solutions, that means there are no free variables, right? So if and only if A has no free variables, right? In other words, a pivot in every column of the matrix A, right? This is not the augmented matrix, right? This is not the augmented matrix. We're talking about the standard matrix. But remember, when we were talking about homogeneous systems, the fact that there are no free variables is the same thing as saying T of x equals 0, right? The homogeneous system, if there are no free variables, means that T of x equals 0 has only the trivial solution. So we're going to start to see here, as we're wrapping up chapter 1, that all these vocabulary terms that we've talked about in different sections, they're all going to start coming together now. We're going to start relating all of these together, and they're going to start to have relationships with one another. These properties are going to have special things together, right? So here's my one-to-one theorem. What does it mean to be onto? T is onto if and only if what? Well, T, recall, we said is a transformation from Rn into Rm. And we said it has to have at least one solution for every possible B in the code domain. In other words, this transformation needs to span. I need to be able to reach every possible vector in Rm. The columns of A, so this happens if and only if the columns of A span Rm, right? So this is all going to start coming full circle. This is all going to start, again, relating back to the past vocabulary we've talked about. Span is appearing again, so make sure you understand that idea. It's going to be super important here. What does it mean to span a space? Well, we know in order to span R2, you need 2 pivots. In order to span R3, you need 3 pivots, so on and so forth. This means in order to span Rm, A must have M pivots. Or to put another way, the matrix A, recall, is an m by n matrix. So this is the same thing as saying A has a pivot in every row. And this really starts to highlight the difference between one-to-one and onto. One-to-one means you have a pivot in every column. Onto means you have a pivot in every row. So sometimes, if it's a square matrix, if A is a square matrix, like a 2 by 2, both could happen at the same time. But if the matrix is not square, well, then you can't possibly have both, right? If it's a 3 by 2, if it's a 3 by 2 matrix, you can have at most 2 pivots. Well, then for a 3 by 2 matrix, that means it's impossible to be onto. If it's a 2 by 3 matrix, well, again, the most pivots you can have is 2, which means you couldn't have a pivot in every column. A 2 by 3 matrix, it's impossible to be one-to-one. So we start to see there are these cases where we can eliminate one or the other. And if you have a square matrix, it's possible you could be both, right? Okay. With that being said, I don't want to keep running for too long. Let's look at today's participation question. So I'm gonna, oh, the camera is doing that. It doesn't. All right, there we go. Okay. We are looking at participation day 7 here. I'll zoom in a little bit. So suppose A is a 7 by 5 matrix with 5 pivots. Okay. 7 rows, 5 columns. It has 5 pivots, which means it has a pivot in every column. So we automatically know before I say anything else, the transformation is one-to-one because it has a pivot in every column. Okay, great. Let T be this transformation where it is A times X. T is then a transformation from R5 into R7. Okay, great. Is T a one-to-one transformation? Well, we just said it has a pivot in every column. Therefore, it is one-to-one. Is it onto? Well, to be onto, it would need 7 pivots. But it only has 5, so it is not onto. So for today, T is one-to-one, but not onto. And that's going to be our answer for today's participation question. T is one-to-one because it has a pivot in every column, and it is not onto because it doesn't have 7 pivots, right? It doesn't span the space that it's going into. It doesn't have enough pivots to do that. Okay, so submit. Okay, great. That's all for today. Homework 2, actually, I apologize. I meant to publish homework 2 yesterday. I'll put that on Canvas today, so I apologize for that. I'll make sure that's uploaded. But I mean, there's only going to be like 1 or 2 questions that were associated with yesterday's lecture, so hopefully that shouldn't put you back too far. But I'll publish that today. If you have questions, let me know. We can talk about it. Also, office hours are available tonight at 6 p.m. via the Zoom link that's on Canvas. So please make sure that if you have questions, you want to talk to me about something. Otherwise, keep in mind there's also the Math Learning Center. They have online tutoring that's free. You can drop in whenever you like, and somebody there will be able to talk to you. Okay, I'll shut up now. Have a great day, guys. Best of luck. I'll see you tomorrow.